The first one is about synchronous games. So I guess this is a type of non-local game which whenever Alice, so I guess, okay, it's a non-local game. And so Alice and Bob have same inputs. And outputs, meaning that the inputs for Alice and Bob are the same and the outputs for Alice and Bob are the same, not that the inputs and outputs are the same. Okay, and then the condition, right, is that, how do they usually write, with V or something? V of A, B, given X, Y is 0. Oh, I should have just done this. X if A is equal to B. So if they're given the same input, they have to get the same, respond with the same output. Okay. And the question is, what is the smallest number of inputs you can have in a synchronous game where you have a perfect quantum strategy but no classical strategy? Okay, so 5 inputs you can do. You can do this magic pentagram game, so maybe the more common one is this magic square game, but there's also this. It's actually a linear system game, okay, where you imagine your variables are these points where the 5 lines of this pentagram intersect, right? So there's 10 variables, right? These 5 in the middle, 5 on the outside. Right? And then your equations or your constraints are the lines, right? So they have 4 variables each, right? And you just need to pick, well, everything's going to be mod 2, right? As they usually are. And then you just pick actually any odd number of lines to be an equal 1 equation, and all the rest to be equal 0 equations. And it doesn't matter which ones or how many you pick, as long as it's an odd number. Then there's no classical solution, of course, just by some sort of parity argument. If I add up all the equations, right, then I get every variable twice. So I must get 0 mod 2, right? But if there's an odd number of equations that are equal to 1, right, then when I add them all up, I get 1 mod 2. Okay. Right, and so, but this does have a perfect quantum strategy, actually, with a tensor product of 3 Pauli, so in dimension 8. And for those, I mentioned this reduction from linear system games to the isomorphism game. But actually, there's also a way, so that's kind of going from like linear systems to graphs, but you can also take a graph and make a linear system, right? So if you take a graph and you let M be its incidence matrix. So the incidence matrix, this means the rows are indexed by the vertices and the columns. Vertices, right? And then the columns are edges. Right? And then there's a 1 if sort of this vertex is an endpoint of this edge. That's the incidence matrix. Okay, so you take M in your linear system to be this incidence matrix, right? And then you just take B to be any vector with an odd number of 1s. Usually you pick a single one. You can think of this as sort of labeling the vertices of the graph with 0 or 1. Okay.
If you're putting any limits on the number of outputs, you're just asking for the least number.
No limit on the number of outputs. Okay, anyways, you can build linear systems from this, and this beautiful theorem of Arkhipov says, so it never has a classical solution, again, by kind of a parity argument, right? Because it's essentially the vertices are the equations, right? The edges are the variables, right? If I add up all the equations, right, then every variable gets hit twice, because it's an edge in a graph, right? So if there's an odd number of 1s in the B, right, then I get this same parity argument. And this beautiful theorem of Arkhipov says that, okay, you get a quantum solution, right, if and only if the graph is non-planar. Okay. And then if you know your minor theory, you know that the two minimal non-planar graphs are K33 and K5, and they're exactly the magic square and magic pentagram. Okay. So that's kind of pretty. Anyways, this answers the question for 5 inputs. You can do it. Okay. Now, for 3 inputs, okay, well, you probably can guess you can't do it. Otherwise, I wouldn't have started with 5 inputs. Okay, so for 3 inputs, so to show that you can't do it, well, probably there's a lot of ways, but the way I'm going to do it, because I like graphs, is I'm going to use a graph, right? So I have my game, right, my synchronous game, and it has this verification function v, which tells me when I win or lose. I'm going to make a graph, right? This game graph. I'm just going to call it x of, let's say that the game was called g, right? What are the vertices, right? So, right, these are just, let's call it e comma x, right? So where this is like an, I guess, an output-input pair. Right, so this is an output from the game, and this is an input from the game, okay? And then the edges, right, so I'll put 2 of these vertices should be adjacent, I denote with a tilde, right? If, I'm going to take the complement of what I do in the paper that I reference in the notes that I wrote, so I have to do that in my head, make sure I don't mess it up. So it's if, when I look at this verification function, I get this, and also okay, so where I swap Alice and Bob. Okay, well, of course, actually, it's a graph, so it's undirected, so I have this if and only if the reverse anyway, so I guess I didn't even need to write that technically. But okay, if I wanted to really make it clear that it's not a directed graph, right, then I need both these things. The reason for this is because actually, if I have a synchronous game and I have a perfect quantum strategy for it, right, then if it's possible to output A, B on inputs X, Y, right, then it's also possible to output BA on inputs Y, X, right, okay, because the players are essentially symmetric, right. So if either one of these is 0, right, then I should never output. Then somehow in the correlations, the probabilities for these should both be 0, right? Because I can't have 1, 0, 1, not 0. All right. So that's the graph, if I remembered correctly, right? And then the theorem is that, okay, G has a perfect, like, whatever strategy, all of the kinds of strategies, well, at least all the quantum ones, right? If and only if the K sub, call it N, X, homomorphism game as a perfect whatever strategy. Yeah, N is the exactly, right? So this Kn X, this is this graph homomorphism game. So this is like, I give you a input from each of the players that input from this graph, right? And then they have to output a vertex from this graph, and I need to, it's a synchronous game, so if they get the same vertex, they have to give me the same vertex. Otherwise, if they get adjacent vertices, they have to give adjacent vertices here, right? Okay. This is the complete graph on n vertices, so either they get the same vertex and they have to output the same vertex, or they get different vertices, they have to output adjacent vertices. Okay. Notably, this is also a synchronous game with the same number of inputs as the original game.
So is this only for quantum strategies?
First, quantum classical strategies, not for non-signaling strategies, I guess. Probably not for non-signaling strategies. Yeah, not for non-signaling strategies.
In all three flavors of quantum.
All the types of quantum ones, yeah. Right. Okay. So so we have this, right? And so then now I have this question about 3 inputs, right? Well, I can now consider, well, actually for an arbitrary number of inputs. Now it's just a question of whether, is there some graph, right, that has a quantum incleak but no incleak, right? Okay, because I mean, if there is, then okay, that's already the game with n inputs, right? And if there's not, then there can't be a game by this reduction. Okay. Now, for n equals 3, it turns out that if you have a quantum 3-clique, you immediately have a 3-clique. Actually, it's true that if you have a quantum homomorphism from any odd cycle to your graph, then you must in fact have an odd cycle of, like a homomorphism from that same odd cycle. Okay. All right. So for n equals 3, like if you have a quantum homomorphism, then you have a classical homomorphism. Okay. All right, so you can't get 3 inputs, right? You can't do it. Okay, but you also kind of can, I should say, because there's a version of the magic square game, right, where you only ask Alice the rows, and you only ask Bob the columns, right? So each person has 3 inputs, right? And you can win perfectly. It's not synchronous, this version of the game, right? The version where each person can get rows or columns is synchronous, but then it's 6 inputs, right? But it is, like, you know, it's essentially synchronous. So it's something called an imitation game, which in a paper was burned we looked at. I mean, any type of game that's one of these imitation games, essentially, well, okay, maybe I should refer to Verne for the sort of higher level QC stuff, but for at least for the Q strategies, it somehow always can be done with this kind of projective measurements and maximum entangled state, and Bob's measurement operators are essentially like determined by Alice's operators. Anyways, but it's not actually synchronous. So. Okay, so then 4 inputs. That's the question. Can you do it with 4 inputs, or can you not do it with 4 inputs? And it's equivalent, of course, because of this reduction to the graph thing, to asking, is there a graph that has a quantum 4-clique, but no actual 4-clique? Okay. And I mean, I guess potentially the answer could be different for Q, QA, and QC. No idea. I'm not really sure why that would be the case, right? But yeah. Yeah, so I really don't have any idea how to prove this or approach it. So, I mean, other than this reduction to the graph case, then okay, that means you only have to look at a particular type of game, so maybe that makes it like slightly easier, but it has, yeah, I mean, the quantum automorphism group is non-commutative, right? But I don't know if this is at all relevant to anything, actually, but it's non-commutative, right? But that actually doesn't allow you to play like the K4 like automorphism game, like so isomorphism from K4 to itself, with a quantum strategy that produces a non-classical correlation. So you can use a strategy where the operators are not commuting, but actually all the correlations that you produce will always be classical. You can simulate, you can produce it with the classical strategy. Okay, so, and that's not trivial to prove. Okay, so this is a paper with me and Simone Schmidt has that result in it, and like it's mostly like a big part of it, Simone, has to do with like some like manipulating just these entries of this 4x4 magic unitary, right? That somehow relate to the probabilities and correlation, and just like, you know, doing substitutions and manipulating them until at some point he gets like, oh, it's a sum of terms that are products of 5 generators, right? And each of those terms is like A, B, C, B, A, right? And so they're all positive semi-definite, and so like this thing is, something is not negative, and that does it, right? But like, only Simone could do, like, sort of, I would have quit after 3, right? Right? So, in fact, I did quit after 3, and I asked him to do it. So yeah. But it's not using anything like, it's not using like a heavy machinery. It's just, you know, it's like, okay, you write down the inequalities, like kind of the facet inequalities for the classical set of correlations, right? And then you show that these must hold for the quantum ones, right? By doing this manipulation and using traces, like, because it must be a trace on this products of these operators, right? You do these manipulations. So that's it. Okay. All right. So that's that question. Maybe Vern has some. He said that maybe it's related to this nuclearity of C-star algebras. So maybe it's something related to that, but I don't know about that kind of thing. So
The complete 4 graph, the C-star algebra is nuclear, even though it's not a PDN. So
maybe somehow related to that.
because they have good dimensional approximation.
Does that change when anything is found?
Is there much link between the these sorts? Yeah, there should be, but then you think
I mean, which sort do you mean exactly? I don't know how. I mean, I guess. Okay. I mean, this automorphism group has to do with, say, if you want to play this KN automorphism game, for instance, right? You could do that, right? And you could take any strategy for that and kind of compose it with a strategy for this. So in that sense, I guess you could maybe say something using that, but I don't know exactly how much that's going to get you or if it's useful at all, right? So, I mean, there's also some relation to like these linear systems and the solution group and the quantum automorphism group of the graphs you get from this reduction to graph isomorphism as well. A paper with my postdoc Yosa about that, and Simone. You mean this graph X has to have some symmetries, or?
Like some non-commutative symmetry that doesn't produce like a new bigger set of correlation.
Mm-hmm.
But you know, at the very least, you should have those symmetries for X as well. Maybe most.
it's just a homomorphism.
Yeah. I don't know if you can glean much about the automorphisms of this graph, right, from homomorphisms from some other graph. I don't know. I mean, this is, in a certain sense, I guess, it's a very kind of innocent question that's like, I don't know, maybe it's not very profound in a certain sense, but also it's sort of like, I mean, we've had the synchronous game for a while now, right? This is kind of, I think, not really been addressed in a certain sense, right? I mean, like, this is kind of a glaring omission, I think, in a certain sense, right?
Strategies, what is the smallest, what are the possible matrix sizes?
I suppose you could do something. I mean, I guess you could also start asking about outputs as well. I have no idea what that's going to do, right? So I haven't even thought about that at all. So, okay. All right. Okay. So the next question was about Hadamard graphs. Okay, so a Hadamard matrix. What's a Hadamard matrix, right? It's a plus or minus 1 matrix. Maybe I should say n by n matrix. Right, so all its entries are either plus 1 or minus 1. Right, and then you have that H transpose equals n times identity. Right, so it's a unitary optiscalar. So I guess, these Hadamard matrices have been studied a lot in sort of like algebraic combinatorics and things like this. I think I remember hearing, maybe I'm misremembering, but it's something like, oh, if you want to take a matrix whose entries are bounded in absolute value by 1, and you want to maximize the determinant, then like a Hadamard matrix is the solution, I think. I don't know. Something like that. Anyways, okay, so these Hadamard matrices, right, they're these nice matrices. Of course, they only exist for n equals 2 and n a multiple of 4, and this big conjecture is that for every multiple of 4 they exist. Okay, and it's not, that's wide open, right? That doesn't really have much to do with this problem. Okay, so what do I care about these for? Because I can build a graph from this, right? So a graph built out of, I'll call it x of h, right? Hadamard graph. Oh, I'm not going to write it again. I just wrote it. That's a title. Right? Okay, so x of h, right? So then, what are the vertices? Right, they're going to be these symbols: r plus sub I, r sub I minus, c sub I plus, c sub I minus. Right, I is from 1 to n. Right, and of course it stands for row and column I. Right. Okay, and then I will make row sub I plus or minus adjacent to c sub I plus or minus if j h I j equals 1, and I make ri minus adjacent to c j minus plus if I get a minus 1. Okay, right? So what this means, in case it's not clear, is that, okay, if the ij entry is 1, right, then I put sort of between these, this r sub I put an edge between r sub I plus and c sub j plus, and r sub I minus and c sub j minus, right? And otherwise, if it's a minus 1, I kind of like swap them, right? I can think of, oh, I have parallel edges or I have crossing edges in a certain sense. Not actually an embedding of the graph, but just in my mind for those 4 vertices, right? I either put them like this or I put them like that. Okay. Also, if you kind of think of the adjacency matrix of the graph, it's kind of like, oh, am I putting in a 2x2 identity or a Pauli X matrix, which is kind of like an encoding of 1 and minus 1 in a certain sense, I suppose. Okay. So this is the graph. It turns out to be a very nice graph. It's something called distance regular, right? So if I take any 2 vertices at distance k from each other, the number of vertices at distance I from the first one and distance j from the second one, it only depends on these numbers I, j, and k. And it turns out that these are all quantum isomorphic. Well, for a fixed n, they're all quantum isomorphic, right? So this is by Daniel Amata, and then independently Bill Martin and Ada Chan. And I should say that they're isomorphic. Like 2 Hadamard graphs are isomorphic if and only if these their corresponding Hadamard matrices are equivalent. So what's equivalent mean? Well, it's not so hard to see that if I have a Hadamard matrix, right, and I multiply a row or column by -1, it's still a Hadamard matrix. Right? If I permute the rows or if I permute the columns, it's still a Hadamard matrix, right? And if I take transpose, it's still a Hadamard matrix. So any of those operations, if I can use any sequence of those operations to get from one Hadamard matrix to another, I say they're equivalent. Okay, so then two Hadamard graphs will be isomorphic if and only if the Hadamard matrices are equivalent. Okay, and then there are, you know, many inequivalent Hadamard matrices, right? So you let the order of the matrix get bigger and bigger, you get more and more. Well, okay, it's not monotone, but presumably asymptotically you get a lot, I guess. I actually have no idea, but already on the 16 by 16 matrices, you get some inequivalent ones. Okay, so then you get a whole bunch of graphs that are pairwise not isomorphic, but are pairwise quantum isomorphic. In fact, it's the first example of more than just two graphs that are non-isomorphic and quantum isomorphic to each other. And there's lots, actually. I mean, presumably arbitrarily many. Actually, I think they specifically say that you can get arbitrarily many of these Hadamard graphs that are all quantum isomorphic. Okay, so that's nice, but the proof is like completely non-constructive in terms of finding the quantum isomorphism. I mean, it actually is well, this one is more in terms of these kind of like these diagrams and these more kind of, I guess, algebraic things. I understand it less, I would say, but like kind of quantum group type stuff. And this one's more combinatorial, but I think it essentially boils down to using this this thing about the planar graphs. At least this one is showing that, okay, any two of these Hadamard graphs have the same number of homomorphisms from any planar graph, and it follows from that. Okay. So in particular, that just proves that they're QC isomorphic. So we don't even know if they're Q isomorphic or QA isomorphic. So I have no idea, right? And it's a bit frustrating because actually there's ways to build quantum permutation matrices out of Hadamard matrices. Right? You can there's a way to take two Hadamard matrices and build a quantum permutation matrix. That doesn't work though. So it's somehow just not the right thing. And so I really have no idea how to construct it or if it's even finite dimensional or what. So it's kind of annoying, I guess. That's the reason I put it as an open problem, because it's annoying me. Yeah. So, but yeah, I don't have any idea how to do it. Again. Well, okay. I don't think I wanted to say anything else about that.
These graphs, if you exchange like the RI pluses with the RI minuses, you change the CIs.
Yeah, actually, maybe I wanted to point out one thing. So that is always a symmetry, right? I mentioned it was distance regular. Also, it's not so hard to show that it's got diameter 4. Right, so the largest distance between any two vertices is 4, and it's exactly the like R sub I plus minus, that pair. Right? And if you swap all the pluses with the minuses, right, then you get a symmetry of the graph. So you always have one non-trivial symmetry, which is unfortunate because you can also find these Hadamard graphs, like some n where there's a Hadamard graph that is classically vertex transitive, right? But there's also one that has just this one non-trivial symmetry, right? But since they're quantum isomorphic, right, and one of them is vertex transitive, they're actually both quantum vertex transitive, right? So they're sort of very, very quantum symmetric, right? But one of them has almost no, has just two classical symmetries, right? If it was just one classical symmetry, then that would be sort of perfect, right? But you can't quite manage to do it. Yeah. So.
Can you elaborate on that? Like, why do you want that?
I don't know, it's just cool. I mean, like, we only recently came up with an example where you have no classical symmetries and some quantum symmetries, right? And so, well, no, I mean, I want still none, right? I mean, in our example, we have no classical symmetry, but some quantum symmetry. I want more quantum symmetry. I want sort of like, at least in terms of sort of the number of orbits, I want the fewest number of orbits possible, right? Okay, then after we get that, then I can say, okay, now I want one that's like sort of quantum rank 3, meaning that there's only 3 orbits on ordered pairs of vertices, right? Okay, and then I can get even pickier and pickier if I feel like it.
There are also constructions using complex Hadamard matrices.
I guess you could probably still make a graph out of it, but I don't know if it's as nice as a graph, and I think someone was talking about this, I think it was Mike, and he says that the proofs don't work. At least I think he was talking about this one in particular, that the proof breaks down. So, I mean, this is really using actually a lot of things very similar to Bob's talk, where he had these two different color spiders, right? Because actually these two different colored spiders kind of correspond to a mutually unbiased basis. And a Hadamard matrix is just a mutually unbiased basis, right? Okay? Because it's, well, the standard basis plus the columns of the Hadamard matrix, if you normalize them. It's two mutually unbiased bases. Okay? And that's sort of what's going on here. Okay, yeah. All right, the last thing I wanted to talk about is maybe I guess it's going to be the longest bit, but well, it's only 10:06, so I can keep talking, I suppose, for now. All right, but this is about something called group, what we've been calling group invariant correlations. Also group invariant quantum Latin squares. Okay, right. So I want to consider, I mean, it kind of is motivated by this isomorphism game. So, okay, maybe I can set it up with some history, right? When we first came up with this isomorphism game, it was back in Singapore, and Antonis Varbitsiotis had seen this homomorphism game, paper of Laura and I, and he was like, hey, we should come up with an isomorphism game. And so we did that, but then the problem was that we could prove a bunch of stuff, but what we couldn't prove is that it wasn't just isomorphism, right? We couldn't actually find a separation. That was sort of the last thing we got before writing this first paper about quantum isomorphisms. So that actually took a few years after the initial idea. And so before that, we were at first just saying, okay, well, maybe we can't get a game where, like an isomorphism game where you can win it quantumly but not classically, but we can at least produce some quantum correlations that are not classical correlations. And so we were just kind of playing around with some constructions for that. And this is kind of related, I guess, in a certain sense stems from that, but over a long period of time. So I only want to look at correlations for isomorphism games, but I don't want to sort of pick some particular graphs that I'm looking at the isomorphism game for, right? I would just say, okay, well, I just consider that both graphs are empty graphs, right? So there's no edges, or both graphs are complete graphs if you prefer that, right? So actually the only conditions that I need to satisfy are these kind of bisynchronous conditions. If I get the same input, I have to give the same output. Okay, different inputs, I have to give different outputs, right? But all the correlations I'm going to talk about here are going to have that property, right? So there'll be the correlation probability will be 0 if those conditions are satisfied. Okay, and then we say, so let's say we have a group G, right? So then we say that a correlation, which is going to have as its inputs and outputs, so I guess, so I should write G to the 4, right? Correlation. Is G invariant if this probability only depends on these two quotients, A inverse B and C inverse D. Okay. Right, so this probability, it's sort of, it doesn't really depend on this full 4-tuple, it just depends on sort of what this quotient is and what this quotient is. Okay? Another way of thinking about this is that, okay, this correlation probability, it doesn't change if I kind of take whatever my output was going to be and I left multiply by some common group element. And similarly for the inputs. Okay, okay, so that's what this G invariant correlation is.
Is there a particular reason that you pick G as your input output? And you could also take input output sets with an action of G, and I guess
You know, I suppose I just, yeah, I mean, okay, you could do something like this, where you are, I mean, I guess the motivation here was like, okay, or part of the motivation at least, or the original motivation is we have some construction which satisfies this property. Right, so let's look at that. Right, but I guess part of the motivation is like, oh, well, if I have a quantum isomorphism between two Cayley graphs for the group G, right, there will also be one whose correlation is G invariant, okay? And so I can just restrict to looking for those. Okay? So there's a particular correlation that's G invariant. I'll call it P sub G. And this is equal to 1 over the size of G if, I think this is right, A inverse B equals C inverse D, I believe. Double check that. Yeah, okay. And 0 otherwise. Okay, so basically what this is doing is it takes your inputs, right? It sees what this difference or this quotient, whatever you want to call it is, and it just outputs a random pair, right, with that same quotient. Okay, and this is classical. Okay, and the reason it's classical is because it's just a uniform combination of the deterministic strategies where I just left multiply by some fixed element. So you give me my input, I multiply it by some fixed element, say A, and then I output that as my output. Okay, so this is just a uniform mixture of all of those. Okay, and this kind of acts as like kind of a projection onto the space of all these G invariant correlations. Okay, I mean this is of course G invariant, that's easy to see, right? And also, I guess this, no, sorry, no, that was right. So if I do this composition, G composed with P composed with G, this is always G invariant. All right, and also P is G invariant if and only if P equals G. Okay. Do people know what this composition is? Or maybe I should write it down. I think Vern did mention it at one point, but it was kind of briefly, I think. So let's just say if I have P1 composed with P2, and I look at, say, B, C, D, I only need to, let's stick to synchronous things for now. But I only need to suppose that the outputs for this correlation are the inputs for this correlation. So this is just the sum over well, P of P1, A comma B given X comma Y, P2, C comma D. So it's kind of like, it's really matrix multiplication, right? if you were to convert these things into matrices. Okay, but another way of thinking about it is like, okay, this is somehow corresponding to some strategy for some game, and this also some strategy for some game. And I just imagine I playing the game for this one first. I get my input. I play according to this strategy. I get an output. Now I plug that output into the input for this strategy, and I get an output. And this is exactly the correlation that you get. So that's what this composition is. Right. Right, okay, so this is just some notation, right? I'm going to use this piece of pi, right? This is just going to be this correlation that corresponds to the permutation pi, right? So 1 if A equals pi of C and B equals pi D 0. Okay, so you're just outputting pi of this or pi of this, depending on if you're Alice Bob. Okay, so these are the deterministic classical bisynchronous correlations, right? And so then the classical bisynchronous correlations, right, are just the convex hull of these things. Pi is a permutation. So I guess in this case of the elements of G. Okay, so not an automorphism of G, just the permutation of its elements. Okay. Right. Yeah, so I mean the set of classical correlations, right, or bisynchronous correlations, right, with inputs and outputs G is just this convex polytope whose vertices are these things. Okay. Actually, I don't know. Maybe this is somewhat interesting, but I mean, if you think of these as matrices, these correlations matrices, this is just the tensor product of the permutation matrix encoding pi with itself. Okay, so it's the convex hull of those. Okay.
So deterministic strategy.
Yeah, this is exactly the deterministic strategy given by pi, right? I mean, like this is the deterministic strategy where if I get some element, I output pi of that element, right? Okay. Yep. Okay, so right, what did I want to say next? Right. Okay, so then since these are all the sort of extreme points of the classical set, right? And because of these things here, right, then that means that if I want to look at the classical G invariant correlations, right, well, the extreme points must be contained in this set. Okay. So this has to contain, so if I take the convex hull of this, that's all of the classical G invariant correlations. Another way of saying that is that every extreme point of this set of classical G invariant correlations is contained in here. Not everything here has to be an extreme point. In fact, it's possible that not everything here is an extreme point. So sort of in practice, you can find this set of G invariant classical correlations. I mean, okay, of course, there's exponentially many of these things, but it's at least not undecidable, something like that. Okay. Now, if I have a G invariant correlation, then I would define this matrix D superscript P. I'm just going to define it entry-wise. So I'll do x, y. X, y. This is going to be p, no, I need to scale. Okay, so this is a matrix. I mean, these G-invariant correlations, they're kind of redundant in a certain sense, right? I don't need to look at the full set of correlation probabilities to tell what it is if I know it's G-invariant, right? Okay, I can reduce it down a lot, okay? So I'm just going to make a matrix, right, which is in a certain sense much smaller than this thing, right, that contains all the information of this thing, right? So I make the XY entry just this correlation probability where this A inverse B is equal to X and C inverse D is equal to Y. I'm going to scale it by the size of G. I think that's right. Double check that. Yes. Because then this is going to be doubly stochastic. Okay. At least for the, I guess maybe I should say that this is quantum correlation or something. That'll be double stochastic. Right.
G times this or G inverse?
No, G. Yeah, so if I sum over X here, right? So if I sum over all AB for a fixed CD, I get 1, right? But now when I sum over X, right, I'm not summing over all AB, right? I'm essentially summing over 1 over G, those things, yeah. So I need to
So you pick your A.
Yeah, I mean, of course, I have to pick one, right? But it doesn't matter which one I pick. Yeah, because it's G invariant. Because, I mean, at least in the quantum case, because somehow, like, also, like, I have this magic unitary, right? The fact that the probability is sum to 1 is that, like, let's say the rows sum to identity, but the columns also sum to identity, right? Because you're bisynchronous, yeah. And if I wanted to, I can generalize this to not just quantum things, but I need to, I need to add some extra condition on them, like doubly stochastic or something like that, okay? But it can be done. Okay, so this is doubly stochastic, but it's not just some random doubly stochastic matrix that just encodes this thing, but it also acts nicely, for instance, like with composition of these correlations that I wrote above, right? So if I have 2 of these G-invariant correlations, I can compose them, it's still going to be G-invariant, right? And what's this matrix going to be for that composition? It's the product of the 2 matrices, right? Okay. And if I didn't have this scalar, that wouldn't be true anymore, right? It wouldn't just be not double stochastic, which would be not as nice, of course, right? I would need to like rescale when I multiply, which I don't want to do. Okay, so that's kind of nice. Right, okay. Right, sorry, I know this was a bit more of a walk to get to the actual problem. This is maybe more of this is more of an average. This is all from an upcoming paper with my former postdoc, Sophia Arnaud-Dautier. So it's a bit of an advertisement of that, I guess, as well. I won't keep you here for 2 hours this time. Actually, be worse for me than for you, because I also have to give a 2-hour lecture at noon on algebraic graph theory. Right. Okay, just for some shorthand, okay, I will let d superscript pi equal to this thing. Right, remember, we know that these correlations are at least contain all the extreme points of my classical G-invariant correlations, right? And I just don't want to write this out every time. Okay, so that's this d pi, and then I can think of I mean, I can replace all the things about the correlations just thinking about these matrices instead, right? It contains all the information anyways, right? And so then, in that sense, the classical set is the convex hull of these things, right? So I would like to understand that, I suppose. Yeah, and so how do I compute this d to the pi? Well, I mean, okay, you can just compute it if you like. But there's two maybe interesting ways of doing it. I need another notation first, so also let p sub a denote the permutation matrix such that p sub a times e sub b equals e sub a b. Right, so this is encoding the permutation, which is just left multiplication by a. Okay. Okay. And I can write down this d pi is equal to the sum over a g of p pi of a, let me double check that, sorry. Yes. I guess I didn't say what this is. This is just a permutation matrix encoding pi. Okay. Okay, so then I need to do this. Okay. So it's just kind of like a uniform mixture of these matrices. And one way of thinking about this is if I can look at this permutation, pi, sitting in like the symmetric group, and I can look at the double cosets corresponding to these translations, right? And then these are the things in the double coset that contains pi that map identity to identity in the group. So it's just a sort of average of all the things from the double coset that map identity to identity. And maybe I should have said that, okay, if I look at this D sub identity comma identity, it has to be equal to 1, actually. Okay? So that's because from the bisynchronous condition. Right? So actually all the other entries in that row and column are 0. Okay, so that's one way of writing this D sub pi. Also, if I define this matrix R, A, comma, B, comma, C, B inverse A, C, then okay. All right, so I can just take this tensor square of this permutation matrix encoding pi, and then I can do this thing, and I get this already. So this is sort of conjugating by this thing is somehow, as I said before, right? The convex hull of these is the set of all classical correlations, actually. Okay, so this is kind of like conjugating by this R, it's somehow like projecting down to the NG invariant ones. All right, so that's classical stuff. I mean, it's still not at all clear somehow, like what this set contains. I think is not. I don't have a good description of this set of classical G-invariant correlations at all. Right? I mean, I know some set that contains all the extreme points, and that's basically it. Right? Right? For instance, if you give me a G-invariant correlation, it's hard for me to tell you if it's in that set or not. Right? I mean, okay, I have to do something which is essentially exponential because I have to just compute for every pi these things and determine the convex hull and tell you if the point you gave me is in the convex hull. Right? I don't have anything more clever to do than that. Right? Okay. But I'm also interested in the quantum G-invariant correlations, right? Which of course are going to be even harder, right? So why should I look at those? And in fact, I already think it's too hard, like to figure out, what are all the quantum, or some sort of description, any sort of description at all of the quantum G-invariant correlations. Right? That seems too hard. So let's restrict to quantum correlations that come from a very special type of object. Okay? And these are quantum Latin squares. Okay. Okay, maybe I should say what a Latin square is first, right? So a Latin square, the classical kind of thing, right? It's like an n by n array where every row and every column has the numbers 1 through n in some order. Okay, so every number appears exactly once in every row and every column. Okay, and then a quantum Latin square, okay? This is an array, but of unit vectors of ij, right? Such that every row or column is an orthonormal basis of some common vector space, I guess. Complex Hilbert space. I don't know what complex vector space. Some common. Let's just say subspace. All right. So typically, you're just going to have that every row and every column is an orthonormal basis of just the full space. But in certain situations, maybe you want to have that. There's just some fixed subspace of some bigger ambient space that you're looking at. Okay. All right. So it's kind of like a quantum version of this Latin square thing, right? Where instead of having numbers, I have these unit vectors, right? And sort of this fact that every row or every column has all the numbers is replaced with, well, every row or every column is an orthonormal basis. Okay. Somewhat natural. And I mean, Gemma, who was here the first week, has a few papers about this kind of thing. Okay, but that's what it is. So I want to look at, okay, but how do I get a quantum correlation out of this, right? Well, maybe you've already noticed that this is essentially a special case of a quantum permutation matrix, right? It's just a quantum permutation matrix where all the projections in the quantum permutation matrix have rank 1, right? Because I can just consider these projections, right? Instead of the vectors, and now I have exactly a magic unity or quantum permutation matrix, whatever you want to call it, but where every projection in there has rank 1. Okay? Because this orthonormal basis condition is exactly the condition that these sum up to identity along a row or a column. Okay, so that's nice. Of course, some information is lost here, right? I mean, like any sort of phase or anything is lost, right? So then I can consider, all right, maybe all the classifying or somehow describing all the quantum G-invariant correlations. That's too hard for me. Let's only consider the G-invariant correlations that come from a quantum Latin square, meaning I take a quantum Latin square, I make this quantum permutation matrix, right? And now to get a correlation from a quantum permutation matrix, I'm just taking traces of products of the projections, okay? So maybe I'll just write it explicitly for the quantum Latin square. If I look at some PIL given J, K, this is going to be equal to, let's say this is IN. Okay. This is going to be equal to 1 over N times, I take psi I j inner product psi L K squared. Okay, so this will be a quantum correlation, a bisynchronous quantum correlation. Okay. So I could say, okay, I want to look only at the quantum correlations that are G invariant and they come from a quantum Latin square, meaning they have this form. Okay, I still think that's too hard, or at least it's too hard for me. Okay? So instead, I'm going to put this G invariant condition directly on the quantum Latin square itself. Okay? Right, so meaning that instead of sort of the correlation being G invariant is some condition on these inner product squares. Right? Instead, I want to put a condition on the inner products. Okay? So so now I think of my quantum Latin square as being indexed by group elements, right? Some group G. Is call it quantum Latin square is G invariant if this inner product psi AC psi B D only depends on A inverse B and C inverse D. Okay, so I take A inverse B, C inverse D. Okay, so when I'm writing the correlation probabilities, I'm taking like this inverse times this, and this inverse times this, but that's because of this sort of like, these are appearing in a different order than the subscripts here, right? I mean, this is like, these two are like these two, right? And then these two are these two, right? Okay, because this is kind of like an input and an output, right? So I have input and output here. Okay, that can be confusing. That's the reason I want to point it out. Okay, so I call this a G invariant quantum Latin square, and now you can really start to say some stuff. Okay, everything before was too hard. Now you can really start to say some stuff. Okay, so I can again, right? I mean, these, by the way, I mean, these inner products, of course, tell me everything about the quantum Latin square up to some sort of global isometry, right? Okay, if I know all the inner products, then I know everything about the quantum Latin square, right? Other than sort of just moving it around unitarily in some space or putting it in some bigger space or whatever, right? Okay, so this is all the real information about the quantum Latin squares here. Okay. And just like with the G invariant correlations, right? I mean, a lot of these inner products are repeated many, many times, right? So I will encode all these inner products in a smaller matrix, right? Yeah, I don't think I need to scale it actually in this case. Okay, so I'm going to make this matrix U, the XY entry, right? So it's again, it's indexed by the elements of G. The XY entry is just this inner product, right? Where I can pick any A, B, C, D I want as long as A inverse B equals X and C inverse D equals Y. Okay, so this is sort of recording all of the different possible inner products here. Again, something to note is that, okay, if let's say X is the identity, right? That means that A equals B, right? And therefore, for this to be non-zero, I must have that C equals D. Right? So if these two are equal, I must have these two are equal, because it's within a row or a column, they're orthogonal. So if either of these are identity, right, then this is 0 unless they're both identity, and then it's 1. Okay? Okay, and then,
If you fix C, for example, you let things are in the basis.
yeah. If I fix one of the indices, vary the other, I get an orthonormal basis. Either one.
So G is the dimension of your basis.
Yeah, the space that they span will have dimension G. Exactly. Or size of G. Okay. U is unitary. And it satisfies also these other two conditions. So if I take the inverse of both entries, I just get the conjugate. That's easy because I'm just swapping I'm just flipping this in. I have to remember how this goes. Okay. This is the easiest one to see. This is not so hard to see. And then you can also do this. Okay? And actually, so I call this the transformation matrix of the quantum Latin square. And a matrix U is the transformation of a G invariant quantum Latin square if and only if these hold. So it's exactly the unitaries that satisfy these conditions. Okay. And also, this is equivalent to saying that if I take U lambda of A, U dagger, which one is dagger? Sorry, B. Where this is the left regular representation of the group. Okay. So it means I have a unitary such that this holds. What's going on here is that these unitaries are precisely the automorphisms of sort of this group algebra spanned by these, that preserve trace and conjugate transpose. Okay? So then you completely characterize these G invariant quantum Latin squares by these transformation matrices, which tell you everything about them, right? Because those things are exactly the trace preserving, conjugate transpose preserving automorphisms of this group algebra.
Things equivalent to.
These three things are equivalent to, I didn't write that U is unitary, I guess, but. Okay.
That's a transpose on the star.
No, that's a star. Well, it's supposed to be a dagger, but I guess I should make it a star. Yeah. Okay, maybe maybe I say this thing because there's quantum group people here. I mean, this is some unitary group, right? So I can write it in terms of intertwiners, surely. Right? Although I guess I sort of knew that in principle, but only realized how to do it last week. Okay, so equivalently, you can just say U is unitary and U satisfies this condition. Okay. And then you can actually, I guess, this thing with the T is essentially that if I get, because of this, I can rewrite this where I have a U bar, right? But I have just the inverse of these things, right? But if I were to just write this like that, and not even have this, right? Then that condition is exactly this condition. So actually, with the bar, it's actually more efficient if you write this one in this other way. Okay. All right. Okay. Sorry. Forgot. Everyone here, we do quantum groups, right? So I also need that U. Yes. U. But this is the swap map. Right? This says that the entries are commutative. Otherwise, I don't know that the entries are scalars. That was more of a joke. Sorry. All right. Okay. Okay, the main thing, why do I care about this U? Other than, okay, it's very nice. It's exactly characterized by these automorphisms of this group algebra. I can also get the correlation from this U, right? So I see my correlation comes from this, right? Where's my 1 over n going to come from? No, I don't need that. Okay, right. So if I were to make this dp, right? Then, okay, this 1 over n goes away because remember we actually scale by, we had to multiply by n to get this d, right? So, okay, actually, this is not in the group invariant form, but right, somehow it would be just this part, right? So actually, sort of the correlation corresponding to this group invariant quantum Latin square, of course, is going to be group invariant, right? And this kind of, let's say, call it the correlation matrix P, is actually just equal to U entry-wise product U bar. Okay. So I guess that already restricts you to unistochastic matrices, double stochastic matrices. I don't know. But still, okay, I mean, in a certain sense, we know very well what these U's can be, sort of, right? But even if you do know that, then what can these D be? That's not so clear, right? I mean, this is certainly not something which is even like basis invariant or something, right? I mean, like, all right, one other nice thing about these U's is that I can compose 2 Latin squares. So if I have some psi ij, and let's call it phi l k, two quantum Latin squares of the same order, I can do what's called a composition, okay, where I make a new Latin square, right, where the entries are, I sum over, how's it go? I guess j, let's say, of psi I j tensor phi j k. Okay, so this is going to be my new ik entry. I have to normalize. Okay, this is going to be my new ik entry. The problem with this is that this is not going to be a quantum Latin square in general. Okay, you'll have that every row and every column is an orthonormal basis, but not of the same subspace. Okay, but what's really cool is that if they're G invariant quantum Latin squares, it will be a quantum Latin square, and it will be G invariant. And this transformation matrix U of that composition is just the product of the two U's for the two original quantum Latin squares. Okay. But this is kind of a very different type of composition than the correlation composition, right? Because for the correlation composition, it's like multiplying these matrices, right? But that, it doesn't commute, like these operations don't commute, right? Like if I take U1 times U2, and then do this interior-wise product with this conjugate interior-wise conjugate, right? It's very different from sort of first taking the products of the unitaries with the interior-wise conjugate and then doing the multiplication, right? So it's really kind of a very different kind of composition, right? And it's invertible as well, right? I mean, like the one with the D's is not going to be invertible in general, right? Because I mean, a double stochastic matrix doesn't have an inverse, right? But this
Quantum Latin square gives you this unitary.
yeah.
Can you go backwards?
Yeah, of course. I mean, I have all the inner products, right?
Yeah. So once you have a unitary, you can get to 20.
Yeah, yeah. I mean, the simplest way to think about it is just pick a basis for like any orthonormal basis for these, where you let, so this is the identity in the group, and then you let A vary. Let that be any orthonormal basis, and then you can just write down what the rest of the thing should be using the entries of the U, because you know the inner product. So you can go back. Okay. The question is to understand the D's. So more specifically, in the case where the group is abelian, okay, things get a little bit easier. Okay. So if G is abelian, like in particular, when are they non-local? When are the correlations you get non-classical, right? That's kind of the question I'm really interested in. Now, if the group is not abelian, actually, there's going to be uncountably many of these U's you can get. Okay? Because I said, okay, they correspond to these automorphisms of this group algebra, right? And for any group, right, I can kind of block diagonalize this group algebra so that it's some direct sum of, you know, a full matrix algebra of size k, tensor identity of size k, right? And those k's have something to do with irreducible representations or whatever, right? Okay. For a abelian group, the k is always 1, right? So you just get diagonal matrices, right? And then the automorphisms of those, then you just get, sort of in that basis, you just get permutation matrices as your automorphisms. But if not, then you can have some bigger block there, and then you can use, you know, essentially any unitary on that block, right? And so that's already uncountably many. Okay. Okay. But if G is abelian, it's easier because it's just, I mean, this group of these U's is just isomorphic to the symmetric group on number of elements of G, right? Okay, I mean, really, it's the symmetric group on the characters of G, actually. Okay, so let's call fancy C the normalized character table. Normalized so that it's unitary. right? So in other words, if I think of the chi A entry of this is going to be equal to, well, 1 over size of G times the character chi applied to A, right? So as a specific example, right, for Zn, right, then this, now I can kind of do an implicit isomorphism that I'm going to essentially suppress, right? This is this omega to the I times J, right, this Fourier matrix, right, where this is some n through the unity, right? Okay. Okay, and then these U's that you get are exactly just C, I'll use star, P, chi, C, okay? These are the U's that you can get, where this is just some permutation matrix, some permutation of the characters. Okay, so there's finitely many of them, okay? And then if you want to find the corresponding double stochastic matrix, you of course just take this, right? And then the question is, okay, well, you know, this is just some permutations, right? For what permutations is this correlation that I get not classical? Or maybe the better question is, for what correlations is it classical? Okay, and I have no idea what the answer is. Okay, if you look at the cyclic groups, it looks like asymptotically it's almost never classical. Let me see if I can find the paper real quick. Well, of course, for small enough n, it is, everything is classical, right?
Yeah, the small size of G, you should be able to just.
Yeah. I mean, if G is order less than or equal to 4, then everything's classical, right? Right? Already for Z5, like there's essentially 8 different correlations, and half of them are classical, half of them are not, right? For Z6, you get 2 classical, 15 non-classical, and so like for Z10, there's 4 classical. Sorry, no. Well, okay, whatever. For Z10, you get 22 classical correlations, 18,714 non-classical ones, right? So, I mean, on the other hand, if you look at Z2 cubed, they're all classical, right? But not for Z2 to the 4th. I mean, I have no idea what's going on, right? If you want the stronger condition that when you look at the corresponding quantum Latin square, right, everything, or I guess the quantum permutation matrix you build from the quantum Latin square, everything commutes, right? Then that's easy, right? Then this pi has to be either an automorphism of the group or corresponds to like a shift, like a multiplication by some group element or some composite, some product of those things. Okay, and if it's an automorphism, then you essentially get out the same permutation matrix, or well, actually, this is an automorphism of the character, so you get out like a corresponding automorphism of the group, right? And if it's a shift, actually a shift of the characters, then you get some sort of, I mean, there's some sort of isomorphism between the group and its dual here that I'm suppressing, okay? One more interesting thing is if I do this, so again, now I'm really suppressing, because this doesn't make any sense. I can't actually do this. Because, I mean, the rows here are not the columns here. Right? No, so I can do that. I can't do this. Okay? So, but if I do it, like if I actually insert like, you know, some matrix which is encoding a isomorphism between the characters in the group here, then what I get out is this d to the pi, which was the classical, this little correlation matrix for the classical correlation, I got, remember this was this E, G composed, P, I composed. Right? The matrix I get from this thing, right? So somehow I start with this pi, actually this is for the characters, and of course this pi is actually on the group, but again, it's up to some isomorphism of the group and its characters, right? So that's sort of an interesting thing, but actually it turns out it's exactly because of, in the abelian case, right? This is B inverse A, right? Which is R, right? And then somehow, if we you put the character table, tensor the character table on one side and the character table on the other side, it just transforms this into the multiplication map. And okay, everything works out, whatever. Okay, but that's the question, I guess. So even in the abelian case, right, we just have some finite number of these pi that give me these different quantum correlations, right? I don't know which pi give me classical ones and which ones give me non-classical correlations. And it'd be interesting to know, I guess. There was a very long explanation for, I guess, a short problem in the end, but I kind of needed to build up a lot of stuff, sorry. But I was asked to talk, so honestly, it's not my fault, so. Yeah. And I guess the other thing is, I would like to know, I mean, I can take, let's say, the convex hull of all these quantum things. It's a finite number, so it is some polytope, right? In the non-abelian case, if I take the convex hull of all the things I get, I have no idea, right? Even for the smallest non-abelian group, the S3, like the symmetrical group of 3 elements, I don't know what's going on. Right? I know that very often it seems that you get non-local correlations, because for instance, if you look at, I pick some big subgroup of some symmetry group of some sort of big giant high-dimensional polytope thing, I don't know. I don't know anything about group theory, so it's some sort of 120 element subgroup of the unitary group or something. Almost all of them were non-local. So that seems to indicate that very often it's non-local, but I don't know what the shape of this thing is. Is it some curved shape? I don't know. So for abelian groups, the things are indexed by pi, for which pi is it non-local? And for some non-abelian group, what does it look like? I don't know. So that's the question. So sorry, I guess it was still under 2 hours though, so only an hour and a half. So, all right. Oh, one more thing I should say. You can do all of this stuff, but with 2 different groups. So where the inputs are from one group and the outputs are from another group. Yeah. Yeah, there seems to be some really pretty stuff going on. I mean, I guess...
These U's you said are
yeah.
If you use the irreducible representations, you know exactly what that algebra looks like.
Yeah, you get this block form, yeah, this direct sum, exactly. You know what it looks like there. So if you have a matrix, it will take sort of like the usual left regular representation and convert it into this block form, right? Now it's very, very easy to kind of pick some automorphism over on that side and convert it back, okay? Because you just conjugate it by this thing that you use to go over there, right? But if you don't have this unitary that moves into the block form, I don't know how to, and I actually don't know how to compute that unitary that moves into the block form. Probably it's known, but it doesn't seem to be some sort of easy closed form for it for a given group, right? I mean, you just have to pick, I mean, what can you do in that block form? You can permute blocks of the same size, right? Or you can conjugate by a unitary on a block, right? Okay. Now, you should, one thing to point out is that, I mean, there are unitaries where this will be an automorphism, right? But won't satisfy this equation, okay? So this is somehow, and that's because they give actually the same automorphism, right? So this is somehow making it so that you pick out exactly one of these U's from each of these kind of classes of things that actually give you the same automorphism, right? Because there are some unitaries that actually pointwise fix this algebra, right? And so if I multiply by one of those, it doesn't change whether it's an automorphism, but it changes this equation. That won't hold anymore. Just make sure that you just get exactly one from each. So you have to be a little bit careful on how you pick them on in this block form, but you can do it. It's not hard.
Another way you could look at things if you use those, the CP maps corresponding to the P universal trace preserving maps.
Mm-hmm.
Those would be acting on M cardinality G.
Mm-hmm.
Your conditions are that you do inner conjugation by lambda G's. The input is invariant under inner conjugation, and the output under outer conjugation.
Hmm.
So some sort of G cross G action on the linear map.
Hmm.
The G cross G invariant linear maps on MG.
Right. Yeah. Mm-hmm.
Again, that suggests some sort of reduction.
Yeah. Yeah, I think there's a lot of pretty stuff going on here, but I don't fully understand the picture. So. You can also use this like left regular representation to build sort of the quantum Latin square. So you can kind of take lambda A times this as your like AB entry of your quantum Latin square. You think of them as vectors. Yeah, I'm actually probably missing, you need to take some inverses somewhere or something like that, but that will give you the quantum Latin square whose corresponding transformation matrix is this U.
Right.
Mm-hmm.
Thanks again.